This recording is going to deal with Newton's third law of motion. It's actually, in my opinion, it's the most difficult among Newton's laws of motion. I think most people, if we ask them about it, even if they don't know it by the number, by the actual title, everyone will tell us to every action there is an equal and opposite reaction. Okay, I'm going to try to make it a little bit more precise by expressing it in terms of forces. So first, the definition of Newton's third law: to every force action, there is a reaction force that is equal in magnitude and opposite in direction. Now, the important thing is these four qualifiers I have afterwards. That's what makes it difficult. Now, the first qualifier: forces always come in pairs at the same time, not a result of each other. Okay, I'm going to go through each one of these qualifiers later on in separate slides to try to explain them more. Anyway, for now, forces always come in pairs. The action and reaction forces act on different bodies, not the same body. They act on different bodies. The third, the interaction, action and reaction, involves only two bodies or objects. No other object is involved. It involves two, no three. A third cannot come into play. Action and reaction between two objects. And then the last qualifier is the action and reaction are of the same type of force. If the action, for example, is a gravitational force, the reaction should be a gravitational force. If the action is a friction, the reaction should be a friction. If the action is a normal force, the reaction should be a normal force. Okay? These are important qualifiers. Okay, now let's start. Okay, we have like this example. If we call this block 1 and this block 2, the force that block 1, so in the subscript we start by writing block 1, exerts on block 2, no matter how their sizes are going to differ, their shapes are going to differ, is going to be equal to the force that block 2 exerts on block 1. 1 is going to be the action, the other is going to be the reaction. I could have started it the opposite way. 1 is going to be the action, the other is going to be the reaction. Now, mathematically, the two forces are equal to each other, but since they are in opposite directions, we have to put the minus sign. Now, one key important thing this is going to be true irrelevant of the state of motion of the objects. We are going to have an action and reaction forces present no matter whether the object is moving, at rest, accelerating, moving at constant velocity, irrelevant of that. Newton's third law is preserved all the time for all possible situations. Now let's start addressing these qualifiers. Okay, I just looked on the web for a picture of someone hitting someone, and I got this one. Okay, these, I'm not sure if it is the correct qualifier or not, but these two gentlemen here, it seems, at a party, and one of them decided to hit the other one. Now, what Newton's third law says, forces always come in pairs at the same time, not as a result of each other. They come in pairs. Now, if Mr. Yellow Shirt is going to go to the police to sue Mr. White Shirt, he's going to say, Mr. White Shirt, the white shirt, had hit me, had assaulted me. Now, Mr. White Shirt can as well go to the police and claim that Mr. Yellow Shirt had hit him or had assaulted him. Now, according to Newton's third law of motion, okay, this is where it is funny. Both are correct. Now, what's the action? The hand exerted a force on the face. What's the reaction? The face exerted a force on the hand. Both of these happened at the same time, not as a result of each other. You cannot say, because I hit the face hit me back. No. As the action is occurring, the reaction is occurring at the same time, not a result of the action. So what that means is, White Shirt can claim that Yellow Shirt had hit him at the same time, and vice versa. So of course, no judge is going to buy that, but the physics is correct. Okay? The forces both hit each other at the same time. Okay? Now, of course, you know that the White Shirt had chosen the location of the hit, chose it on the face, while he got hit on the hand. And the hit on the hand does not hurt as much as a hit on the face. But both of these are of the same magnitude. Now, the other qualifier. The action and reaction forces act on different bodies, not the same object. The action in this case, if we call the action the force exerted by the White Shirt, then that action acted on the Yellow Shirt face. Now, the reaction did not act on anything that belongs to the person who's wearing a yellow shirt. It acted on what? It acted on the hand of the White Shirt person. Okay? Now, what does that mean? The action affected the Yellow Shirt person. The reaction affected the White Shirt person. They acted on two different bodies, not the same object. That's very important. Okay. When a force acts on an object, it affects it. If it does not act on it, it does not affect it. The reaction, for example, does not affect the yellow person. It affects the white person. Okay. Now, what I'm going to do, just show a few examples here. Okay. Now, we have some videos out of sports. Okay, come on. Okay, here you go. Look at that. Now, when there is nothing to hit the ball, what happens? It continues forward. That's what happened in this case. It didn't get stopped. Now, the purpose of a goalkeeper in a game like this is handball. The purpose is to allow the ball to hit him and hit the ball back. Stop it from going forward. See another example here. Beautiful, right? Okay. Let's see an example when there is a reaction. Okay. That's now if the goalkeeper in this case didn't exert a force on the ball, then the ball will continue forward. Now, the effect of the reaction in this case is to make the ball switch the direction of motion and move the opposite way. Okay? Let's try to think of other examples. Let's look at this fellow. Look at that. Running, and look at that. Now, if there is no wall, this person is going to continue moving forward. What did the wall do? The person hit the wall. That's the action. the reaction, the wall hit back this person. Now, the force that this person has exerted, if the wall was flimsy, it would tear down the wall or damage it somewhere. But the reaction did what? Exerted a force on this guy to make him bounce back and somewhat get hurt. So it is the reaction in this case acted on this person, while the action acted on the wall. Now, to convince someone also about the action and reaction, now think about the effects of action. In this case, this is a picture. I was looking for graphics. This is a picture of a demolition ball, kind of that went away and hit the car in the back there. It was not fun, but that's the effect of an action. Now, what is the reaction here? What did the reaction do? It stopped this ball from moving. Oops. Went too far. Now, if you ever hit a soccer ball with the head, you know that it's going to hurt a little bit. So the action is going to be the ball hitting your head and making you a little bit woozy, and the reaction is you are changing the direction of the ball. Okay, that's soccer. Now, what about baseball? Look here what we wear when we play baseball. Why do we wear that? Why do we wear gloves? Because the ball, as it is moving, the force that is going to exert on our hands is going to be strong enough to hit us. So the action to hurt us. So the action is going to hurt us. That's why we wear gloves. Now, as an example, in this case, we have the bat. Look what the bat does on the ball. So we can have some quite strong forces. The ball hits the bat, and the bat hits the ball with an opposite force. We don't see the dent on the bat here because it's made out of different material, stronger material. Otherwise, it's the same thing. Okay, another example here. This picture of someone posted his picture, or his family posted his picture online, saying this is the result of a basketball game. Now, the action here looks like it messed up his teeth. The reaction is, who knows what caused it, but whatever his teeth did either the other person or to the ball that hit him. Okay, these are just examples to show that both action and reaction affect things, but they affect different objects. Okay, now the next qualifier, the interaction, action and reaction involve, we should have the S out here, only two bodies. No other object or the interaction involves. Only two bodies. No other object is involved. Now, for example, here, the blue box. What does it do? It pushes down on the green. What does the green do? Pushes back up on the blue. But the blue does not do anything on the red one. There is no interaction between the blue and the red. Of course, there is the very tiny gravitational force between any two masses, but it's going to be tiny and we are going to ignore it. Additionally, the floor here does not exert any force on the blue one. The blue one does not exert any force on the floor. The only block here that exerts a force on the floor is the red one. Now, the red one exerts a force on the floor, and the floor exerts a force back on the red one. Also, the red interacts with the green one. The green exerts a force on the red, and the red exerts a force on the green. Okay? Always two objects. Don't think of more than two objects. Now, let's take this other example that's trying to stress the same point. What about if I have a push here and pushing on an object? That push is acting on the blue box here. There is no push. This push here is exerted by a person or whatever. That push is exerted on the blue, not on the red. There is no push from here to the red. Now, the only interaction that the red has here is going to be an interaction with the blue, action-reaction pair. Now, the blue is going to push the red forward, and as a result, the reaction is going to be the red is going to push the blue one backwards. That's the action-reaction pair. FBR is going to affect the red block. FRB is going to affect the blue block. Now, FPD, the push, affects the blue block. It does not affect the red block, as a repetition, just to stress it. Now, the last qualifier, the last important qualifier, they have to be of the same type of force. If my action is a push, my reaction should be a push. If it is a pull, my reaction is a pull. But push and pulls are not really good definition of what types of forces. I'm using them here because they are used quite often. If the action force is a gravitational force, the reaction is gravitational force. If the action is a tension, the reaction is a tension. If it is a normal force, the reaction is a normal force. If the action is friction, the reaction is friction, and vice versa. I didn't put the arrows everywhere here for the reverse, but that's absolutely true. Okay, that's important. That's all the qualifiers here for now. We'll pick this up with more examples in the next recording.